Hey there! Tonight we're going to embark on a quiet journey, a slow drift into the very fabric of our world's atmosphere. We'll explore the silent mechanisms that paint our skies and bring the weather. From the softest morning mists to the intricate dance of winds, we'll uncover how it all truly works. Before we dive in, if you're settling in for a mindful moment, consider giving this video a like and subscribing to the channel. It helps us continue these explorations. Imagine waking to a world muffled, softened. The familiar outlines of trees and buildings are blurred, swallowed by a gentle, pearlescent veil. This is the morning fog, a common yet profoundly mysterious phenomenon that has captivated human curiosity for millennia. Everything feels different in the fog. Sounds are absorbed, distant, creating a quiet intimacy. There's a certain wonder in this muted landscape, a natural invitation to ponder how something so tangible, yet so fleeting, comes into being. For our ancestors, such mists were often seen as spirits or the breath of ancient gods. They inspired poetry and myth, a testament to the human need to explain the unexplainable, to find meaning in the world's natural artistry. Long before scientific instruments, keen observers noted patterns. Mists often formed in valleys or after cool nights. They seemed to rise from the ground or descend from the sky, a paradox that puzzled early thinkers. Early natural philosophers began to categorize these atmospheric events. They spoke of vapors, a vague term for something unseen, yet clearly responsible for clouds and rain and, of course, fog. But what were these vapors, truly? The crucial realization would come much later. These vapors were simply water in an invisible, gaseous form. Water vapor, an ever-present component of the air around us, even on the clearest days. We breathe it, we live in it, yet we rarely perceive it. This invisible water vapor is the raw material for all the atmospheric wonders we'll explore tonight. Its presence is constant, its behavior dictated by subtle shifts in energy. Air has a remarkable capacity to hold this water vapor, but this capacity isn't fixed. It changes with temperature. Warm air can hold far more moisture than cold air. This simple principle is key to understanding fog. Imagine a sponge soaking up water. Eventually, it becomes saturated. Air works similarly. When it holds all the water vapor it possibly can at a given temperature, we say it's saturated. What happens when saturated air cools? Just like squeezing that sponge, the air's capacity to hold moisture diminishes. The excess water vapor has nowhere to go. This is the moment of transformation. The invisible water vapor, no longer able to remain a gas, begins to condense. It changes phase, becoming tiny, liquid water droplets. Scientists eventually coined the term dew point. This isn't a place, but a temperature. It's the precise temperature at which air, when cooled, becomes saturated and dew or fog begins to form. Developing instruments to measure humidity and temperature accurately was a slow process. Early hygrometers used hair or other materials that changed length with moisture, a testament to ingenious, patient observation. These tiny droplets are incredibly small, far too small to see individually. A single cubic centimeter of fog might contain hundreds, even thousands of them. But there's another crucial ingredient: microscopic particles in the air. Dust, pollen, sea salt, these act as tiny surfaces or condensation nuclei, where water vapor can easily attach and begin to form a droplet. Without these nuclei, water vapor would struggle to condense, even in saturated air. They are the scaffolding upon which fog and clouds are built, the silent partners in atmospheric alchemy. So how does the air near the ground cool down to its dew point? Often, it's through a process called radiative cooling. As the sun sets, the ground radiates its stored heat back into space. The air directly above the cooling ground then loses its heat to the surface. It chills, slowly but steadily, throughout the night. This is especially effective on clear, calm nights when there are no clouds to trap the heat. A lack of wind is also important. If the air is still, the cool, saturated layer stays close to the ground, allowing the fog to thicken. A strong breeze would mix it with warmer, drier air, dissipating the nascent mist. This type of fog, forming from the ground up on clear, calm nights, is known as radiation fog. It's a classic example of how subtle energy shifts create dramatic visual effects. Scientists often use instruments on tall masts or balloons to study fog's vertical extent. They want to understand how deep the cool, saturated layer is and how it interacts with the air above. Valleys are prime locations for radiation fog. Cold air, being denser, tends to sink and collect in low-lying areas, increasing the chances of the air reaching its dew point. As the sun rises and warms the ground, the process reverses. The air warms, its capacity to hold water vapor increases, and the tiny droplets evaporate, disappearing back into invisible gas. Sometimes the fog doesn't simply evaporate. As the ground warms, it can create thermals, rising pockets of warmer air. These can lift the fog layer, turning it into low-lying clouds. While radiation fog is common, other types exist. Advection fog, for instance, forms when warm, moist air moves horizontally over a cold surface, like warm air drifting over a cold ocean. Studying sea fog requires specialized equipment on ships or buoys. Researchers measure temperature and humidity differences between the air and the water, trying to predict these often dense and sudden fogs. The exact size and distribution of fog droplets are crucial. Larger droplets fall as drizzle, while smaller ones remain suspended, creating that thick, ethereal quality. The way light interacts with these countless tiny droplets creates the visual effects we associate with fog: the halos around streetlights, the way light seems to diffuse and soften. Predicting fog remains a significant challenge for meteorologists. Local variations in temperature, humidity, and wind can make all the difference between a clear morning and a thick, visibility-reducing blanket. Throughout history, dense fogs have stranded travelers, halted ships, and even played roles in military strategies. Their impact on human activity is profound, underscoring the need to understand them. Today, networks of sensors, satellite imagery, and sophisticated computer models help us track and forecast fog with greater accuracy, aiding transportation and safety. Despite all the science, there's still a simple, quiet beauty to a foggy morning. It forces us to slow down, to listen more intently, and to appreciate the subtle transformations of our atmosphere. Fog is just one of water's many incredible forms in our atmosphere. It's a fleeting glimpse of the constant dance between liquid, solid, and gas that shapes our world. The principles behind fog formation, condensation, saturation, cooling are fundamental to all weather. They are the building blocks for clouds, rain, and even snow. Even with all our understanding, the wonder of these atmospheric phenomena never truly fades. Science doesn't diminish the magic, it simply reveals a deeper, more intricate kind of magic. Unraveling the secrets of fog from ancient myths to modern meteorology took centuries of patient observation and incremental discovery, each small step built upon the last. It's a reminder that much of what drives our world is invisible until the right conditions bring it into focus. Fog is just one such example, making the unseen visible. So, as the morning fog eventually lifts, revealing the world anew, we close this first chapter of our atmospheric journey. We've seen how a simple drop in temperature can transform the invisible into a gentle, tangible veil. But the skies hold many more secrets. Next, we'll cast our gaze upwards, far above the ground, to explore the graceful, unseen dance of winds aloft and the mighty forces that shape them. Until then, rest well and keep looking up. As the morning fog retreated, the world revealed itself, yet a new, unseen force began to stir. A gentle breath on the skin, a rustle in the leaves, the silent arrival of wind. It was a reminder that the atmosphere held more than just visible mists. This invisible current, this movement of air, has always been a source of wonder and mystery. For millennia, humans felt its power, saw its effects, yet could not grasp its true nature or origin. It pushed ships across vast oceans, carried seeds, and sculpted landscapes. This unseen hand shaped early civilizations, guiding migrations and influencing the very rhythm of life. Long before instruments, people learned to read the wind's subtle cues. The sway of branches, the direction of smoke, the feel of the air on their faces all offered clues to its invisible path. But what truly was this wind? Was it the breath of gods or a more fundamental, physical force? The quest to understand its essence began with simple observation, then evolved into scientific inquiry. Early ingenuity sought to harness this power. Sails on boats transformed wind into propulsion, allowing distant lands to be reached, trade routes to flourish, and new horizons to be explored. Later, the invention of windmills provided another way to capture the wind's energy. Grinding grain, pumping water, these machines were early testaments to human cleverness in working with nature. These practical applications, however, still relied on an empirical understanding. The deeper scientific questions remained: why did the wind blow? What caused its varying strengths and directions? The answer lay not just in its movement, but in its very presence, the fact that air itself possessed mass and exerted pressure. This concept was revolutionary, challenging long-held beliefs. For centuries, many believed that nature abhorred a vacuum and that air was weightless. This idea hindered true understanding of atmospheric dynamics until critical breakthroughs emerged. In the 17th century, Evangelista Torricelli, a student of Galileo, performed a pivotal experiment. He filled a glass tube with mercury and inverted it into a dish of mercury. The mercury in the tube did not completely empty. Instead, it settled at a specific height. Torricelli concluded that the column of mercury was held up by the pressure of the air pushing down on the mercury in the dish. This was the invention of the barometer, an instrument that could quantify atmospheric pressure. It showed that air, though invisible, had measurable weight and exerted force. Blaise Pascal, inspired by Torricelli, took this idea further. He reasoned that if air had weight, then atmospheric pressure should decrease with altitude, as there would be less air above. Pascal's brother-in-law, Florent Perrier, carried a barometer up the Puy de Dôme mountain in France. He meticulously recorded the mercury level at various elevations. The results confirmed Pascal's hypothesis. The mercury column indeed dropped as the barometer ascended the mountain. This provided undeniable proof of air pressure and its variability. These experiments laid the groundwork for understanding how air density and pressure influence weather. Wind, it became clear, was directly linked to differences in this invisible force. The atmosphere was not a static, weightless void, but a dynamic fluid, constantly under pressure, its movements driven by subtle imbalances. But what created these pressure differences? The answer, scientists eventually realized, was fundamentally tied to the sun. Uneven heating of the Earth's surface became the primary driver. The sun's energy warms land and water differently. Darker surfaces absorb more heat than lighter ones. Land heats and cools faster than oceans. This creates thermal disparities. When air warms, it expands. As it expands, it becomes less dense than the surrounding cooler air. This lighter, warmer air begins to rise, a process known as convection. As warm air rises, it leaves behind an area of lower pressure at the surface. Conversely, as cooler, denser air sinks, it creates an area of higher pressure. Nature abhors a vacuum, but it also seeks balance. Air naturally flows from areas of high pressure to areas of low pressure. This movement of air is what we perceive as wind. The greater the difference in pressure between two locations, the stronger the wind. This fundamental principle explains everything from a gentle breeze to a powerful gale. Thus, the invisible dance of winds is fundamentally a response to the sun's uneven embrace, a constant effort by the atmosphere to equalize temperature and pressure across the globe. But the Earth is not flat, nor is it stationary. Its spherical shape and constant rotation add layers of complexity to these wind patterns, creating grand, global circulations. Scientists, through careful observation and mathematical modeling, began to uncover large-scale atmospheric circulation cells. These are vast, continuous loops of rising and sinking air. The Hadley cell, for instance, describes how warm air rises near the equator, flows poleward, cools and sinks around 30 degrees latitude, then returns to the equator along the surface. Beyond the Hadley cells, other patterns like the Ferrel and polar cells contribute to the intricate global tapestry of winds, each playing a role in distributing heat and moisture. However, these winds do not flow in straight lines. The Earth's rotation introduces a powerful, deflecting force known as the Coriolis effect, named after Gustave Gaspard Coriolis. Imagine throwing a ball straight across a spinning merry-go-round. To an observer on the ground, the ball appears to curve. The same principle applies to air currents on a rotating Earth. In the northern hemisphere, the Coriolis effect deflects moving air to the right. In the southern hemisphere, it deflects air to the left. This explains the prevailing wind directions. It's why trade winds blow from east to west near the equator, and why mid-latitude westerly winds dominate higher up. The Coriolis effect is a silent choreographer of global weather. Understanding these forces required patient observation, mathematical genius, and the courage to challenge intuitive notions about a flat, static world. It was a triumph of scientific deduction. The atmosphere, far from being simple, was revealed as a complex, interconnected system, where every breath of wind was part of a grander, invisible symphony. High above, far beyond our everyday experience, rivers of air flow with incredible speed. These are the jet streams, powerful, high-altitude winds that circle the globe. Discovered during World War II by pilots, these jet streams profoundly influence weather patterns below. They steer storms, guide air masses, and dictate the movement of entire weather systems. Monitoring these invisible currents requires sophisticated tools, weather balloons, radar, and satellite imagery. Scientists track their every twist and turn, refining forecasts. The wind, from the softest whisper at dawn to the mighty jet stream, is a testament to the Earth's dynamic nature. It's a constant, vital force silently shaping our world. As these invisible currents continue their graceful dance, they carry something else, the very building blocks of clouds. Next, we'll turn our attention skyward to witness how these airborne droplets form and how gentle rain eventually begins to fall. As the invisible currents of wind danced across the globe, they carried with them the very raw materials for the sky's next grand performance. High above, suspended giants began to form, seemingly defying gravity, yet constantly being created and recreated. These are the clouds, the architects of our weather, silent sentinels that have inspired awe and wonder throughout human history. Their persistent presence, their ever-changing shapes, posed a quiet mystery. For centuries, clouds were simply clouds, amorphous forms in the heavens. How could one categorize such fleeting, nebulous entities? It seemed an impossible task, like trying to classify dreams. But in the early 19th century, a meticulous observer named Luke Howard brought order to this chaos. A British chemist and amateur meteorologist, he gazed at the skies with a new kind of curiosity. Howard understood that observation was the bedrock of science. He spent countless hours watching, sketching, and noting patterns in the sky, searching for recurring forms amidst the endless variation. He proposed a system, elegant in its simplicity, using Latin terms to describe the fundamental shapes and characteristics of clouds. His work was a quiet revolution in meteorology. He identified cumulus, the heaped, puffy clouds we often see on fair-weather days, rising like cotton wool against the blue. These were the first, most obvious forms. Then came stratus, the layered, sheet-like clouds that spread across the sky, often bringing overcast conditions or a gentle drizzle. They covered vast areas with uniform gray. And finally, cirrus, the wispy, feathery clouds found high in the atmosphere, often heralding changes in weather. They were delicate brushstrokes of ice crystals. Howard's classification, published in 1803, provided a common language for meteorologists worldwide. It transformed the study of clouds from anecdotal observation to systematic science. His work was a testament to the power of careful, patient observation. He showed that even the most transient phenomena could be understood and categorized with diligent effort. But knowing what clouds looked like was only the first step. The deeper mystery remained. How did these vast, visible structures form from invisible water vapor? Recall from our previous journeys that water vapor is an invisible gas. For it to become a visible cloud, it must condense into tiny liquid droplets or ice crystals. Condensation requires cooling, as we saw with fog. But even when air is cooled to its dew point, water vapor struggles to condense into droplets without a surface to cling to. This challenge puzzled scientists for decades. What were these unseen surfaces? What were the microscopic seeds around which clouds could begin their growth? The answer came from Scottish physicist John Aitken in the late 19th century. He built an ingenious apparatus to study condensation under controlled conditions. Aitken's experiments showed that if he removed all dust particles from a sample of air, even when cooled below its dew point, no fog or cloud would form. The water vapor remained invisible. But introduce even a tiny amount of dust, smoke, or other microscopic particles, and suddenly a cloud would appear. These particles were the missing ingredient. He called them condensation nuclei, tiny, airborne specks of dust, pollen, sea salt, or industrial pollutants. They were the indispensable scaffolding for cloud formation. Aitken's discovery was profound. It revealed that the air, seemingly empty, was teeming with these invisible particles, each one a potential birthplace for a cloud droplet. So, with condensation nuclei in place, what causes the air to cool to its dew point, allowing water vapor to condense and form clouds high above the ground? The answer lies in rising air. As air ascends, it encounters lower atmospheric pressure. With less pressure, the air expands. This expansion requires energy, which the air draws from its own internal heat. As a result, the rising air cools, a process known as adiabatic cooling. If this rising air contains enough moisture and cools sufficiently, it will eventually reach its dew point. At that precise temperature, condensation begins. Invisible water vapor transforms into countless infinitesimally small liquid water droplets, each forming around a condensation nucleus. These are the building blocks of a cloud. A single cloud can contain billions upon billions of these tiny droplets, each so small they remain suspended by the slightest air currents, seemingly floating effortlessly. But how do these tiny, suspended droplets grow large enough to overcome air resistance and fall as rain? This was another puzzle that required careful investigation. The primary mechanism in warmer clouds is called collision and coalescence. As droplets move within a cloud, they inevitably bump into each other. Larger droplets having a slightly greater fall velocity can sweep up smaller ones in their path. With each collision, they grow a little bigger, like a snowball rolling downhill. This process continues, slowly at first, then more rapidly as the droplets gain mass and momentum. Eventually, they become too heavy for the air currents to support. Once a droplet reaches a certain size, approximately 0.5 millimeters in diameter, it falls out of the cloud as a raindrop. The sky's delicate balance is overcome by gravity. In colder clouds, where temperatures are below freezing, a different process, the Bergeron-Feindeisen process, also plays a crucial role, involving ice crystals growing at the expense of supercooled water droplets. Regardless of the exact mechanism, the outcome is the same: the gentle patter of rain, a testament to intricate atmospheric processes that nurture life on Earth. Rain is not merely water falling from the sky, it is the culmination of a complex journey, from invisible vapor to microscopic nucleus to growing droplet to the refreshing shower. It replenishes rivers, nourishes plants, and sustains ecosystems. Without this constant cycle, life as we know it would be impossible. Understanding how clouds form and how rain falls involved centuries of scientific inquiry, from Howard's classifications to Aitken's microscopic discoveries. Each piece of the puzzle, patiently observed and meticulously tested, brought us closer to appreciating the sky's magnificent architecture. The clouds above are not static. They are dynamic, living entities, constantly forming, dissolving, and transforming, all thanks to the delicate interplay of temperature, pressure, and tiny particles. From the softest wisps to the most substantial layers, clouds are the visible poetry of our atmosphere, reminding us of the hidden processes that shape our world. But sometimes these architects of the sky do not merely bring gentle rain. Sometimes the atmospheric forces gather with immense energy, leading to a more dramatic, thunderous display. Next, we will explore the powerful charge of storms. But sometimes the sky's architects gather with immense energy. Far from gentle rain, a different, more powerful display begins, announcing its presence with a low, distant rumble. It is the sound of an approaching storm. This primal force of nature, the thunderstorm, has captivated and humbled humanity for millennia. Its raw power inspires both awe and a profound, ancient respect. From the earliest times, the sudden flash and roar seemed to speak of something beyond human comprehension. It was a spectacle both terrifying and magnificent, a true sky symphony. Our ancestors sought explanations in myth and divine power. Thunder was the hammer of a god, lightning a fiery spear hurled from celestial battles above. These explanations, though rooted in wonder, reflected a deep human need to understand the forces shaping their world. They were early attempts to make sense of the sky's fury. For centuries, the true nature of lightning remained shrouded. Was it fire, a magical spark, or something else entirely? The mystery persisted, challenging inquiring minds. Then, in the mid-18th century, a new kind of curiosity emerged, driven by the burgeoning understanding of electricity. Could the sky's fire be related to this new, observable force? Benjamin Franklin, an American polymath, was at the forefront of this inquiry. He observed the similarities between electrical sparks and lightning, sparking a bold hypothesis. Franklin theorized that lightning was indeed an electrical phenomenon. He He sought to prove this with experiments aiming to draw down electricity from storm clouds. His famous kite experiment, though often romanticized, was a carefully planned, dangerous endeavor. He aimed to collect electrical charge from the storm, not to be struck by lightning. Through the wet kite string, he felt sparks and charged a Leyden jar. This demonstrated a connection, hinting that the formidable power of the heavens was indeed electrical. Franklin's work was revolutionary. It shifted lightning from a mystical force to a measurable, understandable physical phenomenon, opening doors for further scientific study. But understanding lightning required first understanding the very clouds that birthed it. These were not the gentle cumulus or stratus, but towering giants, cumulonimbus clouds. These immense storm clouds are born from intense convective instability. Warm, moist air rises rapidly, fueled by latent heat released during condensation, creating a powerful engine. As this air ascends, it cools and water vapor condenses, forming a cloud that can stretch miles high. The sheer scale is difficult to grasp from the ground. Within these colossal structures, a violent, invisible ballet unfolds. Powerful updrafts carry warm, moist air and ice crystals skyward at incredible speeds. Alongside these updrafts, equally strong downdrafts carry cooler air and precipitation towards the ground. This turbulent interaction is the heart of the storm's power. It is within this chaotic environment that the mysterious process of charge separation begins. This is the key to understanding lightning itself. Scientists theorize that collisions between different forms of ice particles are responsible. Graupel, soft hail, and ice crystals all interact within the cloud's turbulent core. When warmer, lighter ice crystals collide with colder, heavier graupel, a charge transfer occurs. The exact mechanism is still a subject of active research. Generally, the lighter ice crystals acquire a positive charge and are carried upward by the strong updrafts to the top of the cloud. Meanwhile, the heavier graupel particles, now negatively charged, tend to fall towards the middle and lower regions of the cloud, creating a distinct separation. This leads to an immense buildup of electrical potential within the cloud. The top becomes positively charged, the middle and lower sections negatively charged. The ground beneath the storm often becomes positively charged through induction, creating an even greater electrical imbalance between cloud and earth. The air itself is a powerful insulator, resisting the flow of this accumulated charge, but its capacity is not infinite. When the electrical potential difference becomes too great, the insulating properties of the air break down. This is the moment of discharge. A sudden, brilliant flash of lightning streaks across the sky or descends to the ground. It is an enormous electrical spark, momentarily equalizing the charge. Lightning heats the air along its path to incredible temperatures, far hotter than the surface of the sun, in mere microseconds. This explosive heating causes the air to expand violently, creating a powerful shock wave. This shock wave is what we hear as thunder. Because light travels much faster than sound, we see the flash of lightning before we hear the thunder. The delay tells us how far away the strike occurred. Scientists use specialized cameras and sensors to study lightning's intricate branching patterns and the speed of its propagation, revealing its complex nature. Research into lightning protection, like improved lightning rods, continues to this day, building on Franklin's foundational understanding to safeguard lives and structures. Thunderstorms are not just displays of power, they are vital components of the Earth's energy balance, redistributing heat and moisture across the globe. They represent the extreme end of atmospheric convection, a powerful reminder of the forces at play in our skies. The science of thunderstorms is a blend of fluid dynamics, thermodynamics, and electromagnetism, a testament to the interconnectedness of scientific disciplines. From ancient myths to modern physics, the journey to understand lightning has been one of persistent inquiry, driven by both fear and fascination. Each flash, each rumble is a powerful demonstration of the atmosphere's dynamic electrical heart, a force we are still working to fully comprehend. The sky's grand symphony of thunder and light is a dramatic chapter in the story of weather, a reminder of its incredible power and beauty. Yet, even in its most intense forms, the atmosphere continues its ceaseless transformations. The energy eventually dissipates and the storm passes. And as the thunder fades, a different, quieter atmospheric wonder often emerges, especially in colder climes. Next, we will explore the delicate whisper of falling snow. As the thunder faded and the sky cleared, a different kind of atmospheric magic often emerged, especially in the quiet embrace of winter. The air grew still, and a profound cold descended. Gone were the violent updrafts and the electrifying charges. In their place, a delicate stillness settled, paving the way for one of nature's most exquisite creations, the snowflake. To witness the first snowflake descend is to see a crystalline wonder, a marvel of natural artistry, each one unique, yet adhering to an astonishing, consistent geometry. Long before microscopes could reveal their intricate patterns, their six-sided symmetry captivated curious minds. This consistent form begged for explanation. One such mind belonged to Johannes Kepler, the renowned astronomer. In the early 17th century, he pondered this very question, publishing a small treatise on the subject. Kepler, known for his laws of planetary motion, was equally fascinated by the simple, six-sided elegance of a snowflake. Why 6 and not 5 or 7? His work Strena su Denive Sexangula, A New Year's Gift, or On the Six-Cornered Snowflake, was more philosophical than scientific, yet it highlighted a profound observation. He recognized that underlying such natural phenomena were fundamental mathematical principles, a notion that would guide future scientific inquiry. Kepler's early fascination laid the groundwork for crystallography, the study of crystal structures, long before the tools existed to truly unravel the snowflake's secrets. His curiosity, sparked by a simple falling flake, revealed how even the smallest natural forms could inspire grand scientific questions. The true marvel of a snowflake's birth lies in a unique atmospheric process, deposition. Unlike rain, which forms from liquid droplets, snow forms directly from water vapor. In extremely cold air, typically below freezing, water vapor molecules skip the liquid phase entirely. They transform directly into solid ice crystals. This happens around microscopic ice nuclei, which are similar to condensation nuclei but promote freezing rather than liquid condensation. They are often dust or pollen particles. The air must be supercooled, meaning water droplets within the cloud are still liquid even at temperatures below freezing. These supercooled droplets are unstable. When an ice crystal forms amidst these supercooled droplets, it acts as a magnet. Water vapor readily deposits onto the ice crystal, causing it to grow rapidly at the expense of the liquid droplets. This process, known as the Bergeron-Feindeisen process, is crucial for snow formation and even for much of the rain that falls from colder clouds. As water vapor freezes onto the crystal, it releases latent heat. This subtle warming effect can sometimes influence the internal dynamics of the cloud. For snow to reach the ground, the entire atmospheric column from cloud to surface must remain at or below freezing. Otherwise, the flakes melt into rain. The journey of each snowflake through the cloud is a unique odyssey, influencing its final form. It grows as it falls, collecting more water vapor. This intricate growth process, guided by precise physics and chemistry, creates the endless diversity of snowflake designs that fascinated Kepler centuries ago. One man dedicated his life to documenting this diversity, Wilson Snowflake Bentley. A self-educated farmer from Vermont, he became a pioneer of photomicrography. From the late 19th century, Bentley spent decades patiently capturing individual snowflakes on glass slides, often in freezing conditions. His makeshift laboratory was a cold shed where he battled the fleeting nature of his subjects, working quickly before they melted or sublimated. Bentley's groundbreaking work produced over 5,000 photographic plates, revealing the breathtaking complexity and variety of ice crystals. He famously declared that no two snowflakes are alike, a statement that, while not absolutely proven, captures the essence of their incredible morphological diversity. The subtle variations in temperature and humidity within a cloud are the master sculptors of snowflake designs. Even tiny differences lead to distinct forms. At warmer temperatures closer to freezing and high humidity, the most intricate, feathery dendrites tend to form with their delicate, branching arms. Colder, drier conditions often produce simpler forms, hexagonal plates, solid columns, or needle-like crystals. Each environmental niche yields a specific beauty. As a snowflake tumbles through different layers of the cloud, encountering varying conditions, it can develop complex, composite structures, a record of its atmospheric journey. This constant interplay of microenvironments and growth rates ensures that each snowflake is a unique crystalline fingerprint of its aerial adventure. When countless millions of these unique flakes descend, they transform the world. A quiet, pervasive blanket of snow begins to mute the landscape. Sounds are absorbed by the soft, porous snowpack, creating an almost otherworldly silence. The sharp edges of the world soften, blurred into gentle curves. This blanket is also a powerful insulator. The air trapped within the snow crystals creates countless tiny pockets, effectively slowing heat transfer. Beneath its white embrace, the ground remains surprisingly warmer, protecting plants and hibernating animals from the harshest cold. The whisper of falling snow is thus a symphony of both delicate beauty and profound ecological significance, a vital part of Earth's climate system. From Kepler's philosophical musings to Bentley's photographic dedication, the scientific journey to understand snow has been one of patient wonder. Each tiny crystal carries the story of its atmospheric journey, a testament to the intricate physics governing our world's weather. The formation of snow reminds us that even the most fleeting and fragile natural phenomena are built upon precise scientific principles. It is a silent, transformative process, turning invisible vapor into tangible beauty, muting the world in its soft, insulating embrace. With the whisper of falling snow, our exploration of atmospheric wonders nears its end. We've journeyed from morning fog to thunderous storms, revealing the intricate dance of our planet's air and water. Next, we will reflect on the grand tapestry of weather and the enduring human quest to understand it all. Tonight, we take a reflective pause. We've journeyed from the soft hum of morning fog to the delicate whisper of falling snow. Each atmospheric wonder, explored in its own quiet detail, seemed a separate, beautiful mystery. We've sought to unravel how invisible water vapor becomes a tangible veil, how air pressure differences sculpt the unseen winds, and how countless droplets coalesce into gentle rain. We've delved into the electrifying charge of thunderous storms and admired the intricate geometry of a single snowflake. But as we reflect, a deeper truth emerges, weaving all these phenomena together. The morning fog, forming as air cools to its dew point, is not an isolated event. It is a local manifestation of the broader atmospheric ballet where temperature and moisture are constantly in flux. The graceful dance of winds aloft, driven by the sun's uneven heating and the Earth's rotation, carries the very moisture that feeds the fog and later, the clouds. The formation of clouds dependent on rising air and microscopic condensation nuclei is a direct consequence of these winds lifting moist air to cooler altitudes. And gentle rain, whether through collision and coalescence or the Bergeron process, is simply the atmosphere's way of returning condensed water to the Earth, replenishing its cycles. Even the thunderous charge of storms, with their powerful updrafts and charge separation, are extreme expressions of the same convective processes that build smaller clouds. And the whisper of falling snow, forming directly from vapor into intricate crystals, is a colder, quieter version of the condensation and precipitation dance. These are not separate acts but movements in a grand, interconnected symphony. Each note, each pause, each crescendo relies on the others to complete the composition. This realization led to the development of meteorology as a truly holistic science. Early observers looking at isolated events gradually began to piece together the global picture. The challenge was immense: how to integrate countless local observations into a coherent understanding of a planet-wide, ever-changing system. It required a global effort, a network of patient observers sharing their data, slowly building a collective consciousness of the atmosphere's intricate workings. The invention of the telegraph and later radio allowed for near real-time communication of weather data, a breakthrough for understanding moving systems. Weather balloons launched daily from sites around the world began to probe the upper atmosphere, revealing the vertical structure of temperature, humidity, and wind. Radar provided eyes into storm clouds, showing the intensity and movement of precipitation, allowing for tracking of severe weather. But it was the advent of satellites that truly revolutionized our view. From space, we could see entire weather systems, vast cyclones, and global cloud patterns, all in motion. This confirmed a profound truth: the Earth's atmosphere is a single, vast, interconnected fluid system, constantly in motion, ceaselessly exchanging energy and matter. A change in one part of the world can ripple outwards, influencing weather thousands of miles away. It's a testament to the intricate feedback loops that govern our planet. The global energy balance driven by the sun is constantly being redistributed by these atmospheric currents, from the equator to the poles, from the ocean to the land. This deeper understanding fueled an ongoing quest to predict and understand weather with increasing accuracy. It moved beyond simply describing what happened to forecasting what would happen next. The birth of numerical weather prediction in the mid-20th century was a monumental leap, translating the physics of the atmosphere into mathematical equations. Early attempts were limited by the computing power available. Solving these complex equations for the entire globe was a task of unimaginable scale. But with each decade, computing power grew exponentially. Algorithms became more sophisticated, capable of resolving finer details of atmospheric processes. Supercomputers, vast engines of calculation, became the heart of modern meteorology, simulating the atmosphere's future state hour by hour, day by day. Data assimilation became crucial, continuously feeding real-time observations from satellites, balloons, and ground stations into these models, refining their starting points. Ensemble forecasting, running multiple models with slightly varied initial conditions, began to quantify the uncertainty inherent in atmospheric predictions. This acknowledged the butterfly effect, how a tiny, unobserved perturbation can, over time, lead to vastly different outcomes, a profound limit to long-range predictability. The quest continues, a ceaseless effort to refine models, improve observations, and push the boundaries of what we can know about tomorrow's sky. From short-term forecasts to seasonal outlooks, the accuracy has improved dramatically, a testament to generations of dedicated scientific work. This journey through the atmosphere reveals the profound beauty of scientific inquiry itself. It is a testament to human curiosity, perseverance, and the relentless pursuit of understanding. From ancient philosophers wondering about the breath of gods to modern scientists coding complex climate models, the spirit of inquiry remains the same. It is a process of constantly refining our understanding, chipping away at the unknown, only to reveal deeper, more intricate layers of nature's wonders and complexities. There is a humility in this work, a recognition that for all our advancements, the atmosphere remains a vast, dynamic system with enduring mysteries. It is a living, breathing entity, full of intricate feedback loops and chaotic nuances that continue to challenge our predictive capabilities. The sleepless scientist, whether observing fog on a cold morning or analyzing satellite data at midnight, is part of this unbroken chain of human endeavor. And so we end with a sense of calm appreciation for the dynamic, living sky above us. It is a canvas of constant change, a source of life, and a perpetual wellspring of wonder. Its enduring mysteries do not diminish our understanding, but rather deepen our respect for the forces that shape our world, inviting continuous observation and thought. The cycle continues from the gentle hum of morning fog to the whisper of falling snow, a ceaseless dance of water and air, energy and matter. And so, as the moon climbs high, sleep well, knowing that the sky above you, in all its complexity and beauty, is always telling a story, always in motion, always waiting to be discovered anew.